start today's. Maybe you can remove this. Got it. Okay. So today it's pleasure to have Sébastien Palcoux, who is going to say why should we study simple integral fusion categories. Good.
Yeah. Thank you. Yeah. So I will try to explain or to convince you why we should study such a category. And in fact, I will answer the question immediately. So the reason why we want is to to find some specific exotic quantum symmetry. So exotic quantum symmetry already exists, but specific here, whoa, it's not very, yeah, specific will be, in fact, in some integral case. Yeah, and in fact, I will explain in what sense such an exotic quantum symmetry will be the same thing as meeting an alien. So it's so unexpected that it's yeah. But yeah, if you can find that such mathematical aliens don't exist, it will be still very, very interesting, but less exciting. I'm much more interested in aliens anyway. Okay, so I talk about quantum symmetry, in fact, exotic quantum symmetry, but what is a symmetry? Classic, usual symmetry. So usual symmetry is a transformation that preserves an object. In fact, I can put here. A symmetry is a transformation preserve an object. So for example, and the set of symmetry form a group. So here is an example. You take the triangle, the regular triangle, and you have 1, 2, 3, 6 symmetry, in fact, isometry here, preserving the triangle. And it forms a group in the sense you have such a table here. And in fact, more generally, every finite group can be an isometric group of some polytope. So, in fact, the notion of symmetry is essentially the same thing as the notion of group. Okay. Okay, so now what is a quantum symmetry? So we said symmetry is like group, so we can say, okay, quantum symmetry is quantum group. But no, we will not use this term. We will not talk about that. In fact, you can talk about quantum group. You can also, more generally, of algebra, tensor category, subfactor, planar algebra, etc. We will start by a notion which is much easier to introduce. In fact, we will slightly augment the notion of group by the notion of fusion. Yeah. So the fusion here is designed to look like what you have in when you collide two particles. You have two particles collide. You have a fusion, and then you have many other particles. And this is the point of this, this rule here. You have two particles, Bi, Bj, and then after the collision, you have many particles with some multiplicity here. And this multiplicity is an integer. So I said it's an augmentation of the group structure because if you take this multiplicity to be trivial in that sense, so it's not zero except for one element. It's exactly it recovers exactly the group structure up to this axiom. So these three axioms are the axiom of a fusion ring, and these three axioms, in fact, exactly generalize the notion of the axiom for a group. You have the associativity of the group, you have the existence of a unit, and this generalizes the inverse. So here we talk about the dual, and you have this extra property, but it's okay. So it's exactly group structure generalization. So it is called fusion ring today. In fact, this comes from Lustig in a paper in 87. Okay. So example. So the group
The BIs are elements of a free algebra.
BI are the basis,
The basis of
element of the basis
of
of
a
the ring of the ring. Yeah, it's
just
a
finitely generated.
yeah, it's a
infinitely
yeah, it's a finite basis.
finite.
It's a free Z ring. So the fact it is finite is important. Okay. So example. So this case, in fact, is exactly the group ring where the basis is exactly the element of the group. But you can make another class of example coming from. I have some difficulties with this thing. I like that. Yeah, use the end. Yeah. So the the character ring. So if you consider the irreducible character or the irreducible representation, you can generate, in fact, such a fusion ring also. And in fact, I will explain there are many other such fusion rings in general. And in fact, yeah, we are interested in fusion rings which are not of this form. Okay. So in fact, one easy way to see that there are many others which are not of this form is that you can generalize the notion of dimension as the degree of the character here, and we will explain that you can have some non-integer dimension. So a fortiori, this cannot come from a group, in fact, a finite group. So you take the fusion ring and you take the basis, and there is a theorem due to Frobenius and Perron. There is a unique way to get a dimension. So there is a unique star homomorphism, which is positive on the basis, like that. And so this, in fact, this is called the Frobenius-Perron dimension, and it turns out that if you take the coefficient I showed before, this coefficient, this you can make matrices, fusion matrices, and in fact, this Frobenius-Perron dimension are exactly the norm of the fusion matrices. So in particular, they are algebraic integers. If you make the sum of the square, it's the Frobenius-Perron dimension of the full fusion ring. In particular, for this case, it's exactly the order of the group. Okay. So we are interested in the case which is called one Frobenius. We have such divisibility. So this quotient is always an integer or an algebraic integer if you work out of the integral case. And this is motivated by a conjecture by Kaplansky called 6 Kaplansky conjecture.
但是啊，这里可以了，安排好了，是不是啊？11点的话，你有足够的时间了。但是稍微晚点或早点都没事，反正都说好了，就早点啊，这样保证你那边时间。我8点半搞到10点就差不多。10点我们就往那边走了。好。那是一个3D最好的职业，是个院士，那项职业，文职少将，对的啊。做这个要做的，他就是做泌尿的，不是他可能只对手要做的。你搬冤尸体的推选的是吧？加的一个办法，是吧？看吧，反正看吧。好，我看看吧，这个东西给我越想要严重一点。
Mute. That would be really cool if I could. You have to unmute yourself.
And wait, where is my son?
This is your.
Ah.
Talk.
This second slide, the theory or
I think it's okay. The second is okay. Go ahead. It's unmuted already.
Hello?
No, but it's okay. There are top left on.
Ah, okay.
Oh. Go ahead. Should be fine.
Okay.
second slide, the theory or property or this
Second line, this one.
sum of square of the
This is the definition. It defines the global Frobenius point dimension of the. This is the dimension for the basic element, and this is for the. Yeah. So how can I remove this? The Control L, no? Click somewhere. Right. That's yeah.
So Frobenius parent dimension of BI.
Yeah.
Do you mean you take one basis element BI?
Yeah.
You look at intersection or fusion with all other basis elements, look at that matrix, take the norm. That's that. Okay. All right.
Yeah. Anyway. So yeah. Okay. So motivated by Kaplanski conjecture, we are interested in this case, which is not always true, this divisibility. So we recover the group case, in fact, is when the dimension is one everywhere. It's called the pointed case. But if you're interested in something non-integer, there is this example. So for this notation, I call the rank the order of the basis, and the type the sequence of the dimension. So if you consider this small example of rank 2, and you take this rule, this B2 square equal B1 plus B2. In fact, the Frobenius point dimension is a homomorphism. So you recognize the famous equation x square equal 1 plus x, which the root is a golden ratio. So you get an object of dimension, the golden ratio. Here is another object of dimension, the golden ratio. It's, well, Hausdorff dimension golden ratio. It's this called the dragon, golden dragon. So I don't know any, I guess there is a connection, you can, but I don't know any connection between these two objects. But there should be. At least the dimension is the same. Something more, okay. Yeah. No, that is not more. This is not working. Okay, can you, no, the B1 is a trivial. B1 is a. Yeah, can you put the full screen as to remove this? Yeah, and now is it working? Yeah. Okay. Yeah, so B1 is trivial, so you don't need any other relation. Okay, so this is for non-integer, but the title was integral. So integral means integer. So we are interested in the integral case. Integral case means that all the dimensions are integer. So for example, the character ring of the group ring are integer. Here the dimensions are the degree. And in fact, we are also interested in simple. And here simple is the generalization of the notion of simple group. And here you just need to assume that there is no proper non-trivial fusion subring. And subring means you have a subbasis generating the fusion ring, etc. And so, in fact, so the character ring is simple if and only the group is simple. So you already have many examples of simple integral fusion ring coming from the classification of a simple group. And in fact, simple integral fusion ring, which are not of this form, can be seen as extension of this very famous table. So this is nice. And in fact, there are plenty of examples. Too much. But this is only fusion ring, and we expect something more substantial as a quantum symmetry. Just fusion ring is not enough for a quantum symmetry. We need some categorification. So you have the fusion ring, group ring, character ring, and there is a notion of categorification. And then here, the categorification of the group ring is called vec_G, the category of a vector space, G-graded vector space. The categorification of the character ring is rep_G, the category of representation of the group, etc. And you can come back if you want, if you have a, so the categorification of the notion of fusion ring, notion of fusion category. And you can come back by the Grothendieck ring, you have fusion category, you can get a fusion ring. So this way is unique. This way is I can have 1 or 0 or several 1. Okay, so what is the so I will not define in detail what is a fusion category, but I can explain briefly the, in fact, there is a notion of categorical associativity. So you have the fusion ring, you have the associativity, but in the categorical level, you want more. And the basic category with this categorical associativity is called a monoidal category due to MacLane. And so you have morphism for the associativity like that of object, tensor product. And this morphism should satisfy the pentagon diagram like that. So yeah, this should commute. And why that? Because otherwise you can have some ambiguity. You can. This is for removing the ambiguity. Okay. But so there, in the monoidal category, there is a tension between the notion of skeletal, where two objects are the same if only they are isomorph, and the notion of strict, where the morphism for associativity is trivial. You cannot have both these two notions. There is a tension, and this is this tension. Because of this tension, you cannot categorify everything. If you can have both, then you can categorify everything. Because of this tension, you have to put some non-trivial associativity morphism, or etc. Okay. So, in fact, if you generalize a bit the example I showed before by putting an n here, in fact, this admits a categorification if and only if n equals 0 or 1. So the golden fusion ring can be categorified, in fact. Okay. So, okay, so now the point is the existence of exotic integral example. Yeah. Yeah. So here is 3 statements about integral example, exotic integral example. So in fact, an integral will be called exotic here if it is not, if it cannot be cooked from group theory. And in the theory, this means weakly group theoretical. So when you say something is weakly group theoretical, it means you can generate this from group theory in some sense. Maybe the sense is written here. So this is 3 statements which are open. Every integral fusion category is weakly group theoretical. So integral means come from group theory in some sense. It is open. And here it's the simple case. And here it's the modular simple case in some sense. And in fact, because it's modular, you can replace weakly group theoretical by pointed. So you have a statement which is, yeah, every simple integral modular fusion category is pointed. So this is an open question, one of the big, most important open question in the fusion category theory. So is there an integral fusion category which is not weakly group theoretical? And in fact, so this is asked here. And so if you are in the simple case, in fact, weakly group theoretical is the same thing as group. Yeah, that's why. Here there is no weakly group theoretical. And in fact, we asked whether these two are equivalent. So you can reduce this famous problem to the simple case. And we prove that these two are equivalent. So we ask whether these two are equivalent, and we prove that these two are equivalent. So you can reduce to modular case. And we checked that this is true up to rank 13 like that. So I talk about modular. So what is modular? So modular is explained here, is in this box about categorical commutativity. So in the previous slide, I explained what is categorical associativity. Here, if you want commutativity in a categorical framework, you need more than just commuting object for the tensor product. You need a morphism, and you need an hexagon diagram to remove the ambiguity. So I did not draw the hexagon diagram. Now, if you have that, it's called a braided category, and you can make this matrix called the S matrix. So you have this picture. This is one braiding, another braiding. You take the trace of that, and the entry are X and Y are simple objects, and you get a matrix. If this matrix is as easy as possible, the rank of the matrix is as small as possible, which means this is equivalent to that. So it is, in some sense, the trivial case, and this is exactly also the group case, as a rep G group case, due to the limit. And perpendicularly, in fact, in the opposite side, you have the modular case, which is where the matrix is invertible. So these two words are completely opposite. And so here you have the notion of a modular tensor category introduced by Moore and Seiberg. So there are many, many things to say about modular tensor category. I have no time. The notion of Drinfeld center, of topological quantum field theory. You have many, many simple examples coming from Lie theory, which are non-integral, in fact. Vertex operator algebra, representation of SL2Z, the modular group. That's why we call that modular tensor category. Okay.
What was D of X? Sorry. D of X was
D of X.
What is D of X?
Ah, yeah, it's just a simplification, just the dimension of X.
Over
the Frobenius point dimension. Yeah. Yeah. Yeah, you can generalize that to positive characteristic. In fact, there is a categorical dimension, which is not necessarily the Frobenius point dimension, but it is when it is the case called pseudo-unitary. We are interested in the integral case is always pseudo-unitary, so no problem. Anyway, so as I said, we are interested in, so exotic here means none coming from group, in the simple case exactly. So we are interested in classifying simple integral fusion rings, which are not of this form. So we can prove that there must be of rank greater than 4. If we have this assumption coming from, no, in general it's great. In general it's like that. Yeah. greater than 4. We have example of rank 4, but if you have this assumption coming from Kaplanski, we found no example of rank 4, but only from 5. But infinitely many of rank 4 without this assumption anyway. So if you assume this Kaplanski assumption here, we found so many examples. So under this bound, so you have the rank, the bound for the Frobenius parent dimension, and the number of fusion rings we found. So in total, we found 505 fusion rings. But among them, only 8 come from group. So you have plenty of room for something not of this form. But if you apply quantum Fourier analysis, you can exclude 95% of them from unitary categorification. And so up to now, we will be interested only in unitary categorification. Of course, you can ask whether there is a non-unitary, but yeah, unitary. But there still remain many of candidates. Yeah, 20 candidates. So here is what I mean by quantum Fourier analysis. So you, in fact, you can get a unitary categorification criterion of this form, which depend only on the norm of the matrix and the matrix tensor product like that. And you have a big matrix which should be positive like that. This depends on n, and if n equals 3, it's called, the fusion ring is called 3 positive. And this is our unitary categorification. And we found 21 which are 3 positive. So we have 20 candidates for to find our mathematical alien. Okay. And we found that this example can be made using the character ring, but by small perturbations, small transformation called interpolation, isotypical variation, or contraction. Okay. And I ask whether it's always the case, but I hope not. But in any case, even if it is true, even if you can find of this form always, the categorification problem remains. So here are the 3 first candidates for rank 7, 8, and 9. And the first 2 was already excluded. By the first by this method, I will explain. The second by this method, and the third is still open. But you are so. In fact, this is you can see this as a challenge. In fact, you have 20 candidates, and you need to find new theory to exclude it, because you cannot exclude it by known theory. You have to create a new theory to exclude it. And in fact, we created these 2 new criterion to exclude the 2 first candidates. So let me explain briefly what I mean by these 2 criteria. And it's already 5.5.
How should I read this positivity condition?
How should you?
How should I read it?
Read. It's a positive matrix. So it's a matrix.
Oh, it's the positive matrix or something.
Yeah.
Okay.
Yeah. So let me explain the first by a picture. This by a picture, and this one I will do it briefly, and then I will display this example, which is open. So in fact, this okay. So so the categorification problem, you have the pentagon axiom. You can reformulate the pentagon axiom as a system of polynomial equation. You can visualize the variable as a tetrahedron. And in fact, the equation comes from evaluating by 2 different ways a triangular prism, illustrated like that. You have a triangular. So everything is in the categorical framework. So the edge, the vertex are labeled by morphism, and the edge are labeled by objects. So this should be a labeled triangular prism. But in a picture in a paper of Dylan Thurston, which is not about category but about graph theory, this illustrates exactly the proof of this way to see the pentagon equation, the system of pentagon equation. You evaluate in two different ways this label triangular prism, and you get something, a product of three things equal a product of two things, up to taking a sum. So, yeah. And so we can use this pictorial representation to better understand the system of pentagon equation. So first, we prove that this way is equivalent to the system of pentagon equation. But using this picture, this is good to have some insight, to have some symmetry, and we were able to find a subsystem of the pentagon equation. So the full pentagon equation is here for this example, is like something like 50,000 variables and 2 million equations. So it's really too much to solve it directly, even to find by brute force a subsystem, it's too much, you cannot do it. So thanks to that, we are able to find a subsystem of 12 polynomial equations and 10 variables, which was used to exclude. So this one has a solution, but we found another one with solution and an extra equation which can connect the two, and there is no solution. So it was done for that. Next. So I will not read this one because it's too complicated, but this is a reformulation of the existence of an equation, the pentagon system of this form, x, y equals 0, with x and y different from 0. So you have the system of pentagon equation, and you say, what if there is an equation looks like of this form? Then there is no solution, and you can reformulate this as this like that, only in terms of the fusion coefficient. And so you can exclude the second candidate like that. And here is the third candidate, which is open. And you see, so this is an isotypical variation. So same type of the character ring of PSL28. So here you have, so the first is PSL28. And here, the small variations are in the yellow part. So in fact, they are not equivalent. It's it's an open problem whether it can be categorized. And the application of the localization strategy provides a system of 45 polynomial equations and 34 variables. But it's still open whether this system admits solution. I need a bigger computer, in fact. I apply for a grant for that, in particular. Okay, so this is almost the last slide. So what about the future? So assume you can find this mathematical algorithm. So this will generalize the classification of finite simple groups. So you can already do that at the fusion ring level. As I said, there are plenty of examples. It's not enough substantial, and we want to do that at the categorical level. So at the categorical level, we don't know whether it exists or not. Assume it exists, then you, in fact, in some sense written here, such exotic quantum symmetry can generalize the set of prime numbers. Because, you have, so without going into the details, in fact, my initial motivation was that. So I did not introduce that, but like there is this class of object in a subfactor theory. If you take the representation of that, it is exactly a simple integral fusion category, which is not weakly grouped theoretical, which is exactly what we are looking for. And in fact, this class whose existence of object is unknown, but the only known example in this class are the one coming from prime number. So if we can find the exotic example, then the next step is to look whether it comes from, in fact, of algebra. This can be reformulated in the word of algebra, finite dimensional of star algebra without proper non-trivial F coaddition, blah, blah, blah. That doesn't matter. So it's, yeah, this is interesting. So you say, okay, you can extend the notion of prime number, but there is a very famous conjecture related to prime number, the Riemann hypothesis. What about generalizing the Riemann hypothesis, the quantum? And in fact, for fun, I did it, but I want to say it's not very substantial. There is a way to generalize the Riemann hypothesis in the subfactor framework, or in fact in the fusion category framework. But thank you.
Questions?
Thank you. So what do you mean by categorification? I mean, are we seeking for a fusion category that is simultaneously strict and skeletal?
No, I said this is not possible in general. That's why, if it is possible in general, then every fusion ring can be categorized. Strict and skeleton is not possible in general. There exists some categories which are like that, for example, the pointed one, but in general, it's not possible. So categorification means you can say you have a fusion ring and you want a solution of the system of Pentagon equation. That will be a categorification.
Okay, so any fusion category that its underlying fusion ring gives the ring is a categorification of our fusion ring, right?
Yeah, if you have a fusion category, you take the Grothendieck ring. It's a fusion ring, and this initial fusion category is a categorification of this.
I see. Thank you.
So maybe as a follow-up to this question, so you can look at the categories where this pentagon, hexagon is satisfied not exactly, but up to scalar, like a projective representation things. So have you looked at that? Does it help you categorify the fusion algebras?
So if the system is not satisfied exactly, then you can categorify it, but it will not be a fusion category. It will be something more general. In fact, you can categorify a fusion ring by something more general as a fusion category. You can categorify it by a tensor category. You don't need to assume fusion category, assume semi-simple, for example. But the tensor category is not semi-simple in general. So you can see, okay, there is no fusion categorification, but maybe there is a tensor categorification. And there are many, many other things. For example, there is a notion of lax tensor category where the associativity morphisms are not invertible. There should be isomorphism, I said, but in general, if it is not invertible, it's called a lax tensor category, lax monoid. And what you said, maybe a projective, it's another way to generalize, but it will not be a fusion category. I did not look to what you are talking about, but I should try. In fact, the projective, I should apply my local system to the semi-simple? Lax. Ah, yeah, like non-invertible. No. In fact, I asked an expert whether there exists generalization of fusion category with this lax. The expert don't even know if it exists. But no, very few people, in fact, look at that.
More questions? So this is a slide of yours about Thurston. Can we go to that? The slide with the good, nice pictures. Thurston's thing.
The first slide.
Thurston.
Ah, Thurston. Okay.
Okay. Dylan Thurston. Yeah. Okay. So I was trying to kind of learn it from here. So
yeah. So in fact,
So what are these arrows?
What are these? Oh, so yeah, you just you transform this like that and this like that. So
But the rule doesn't come
Yeah,
from
so-
any fusion. I tried to tensor those tetrahedron to each other, get any of these, I couldn't.
no, in fact, for example, here there is an extra loop which is not there.
Right.
Because adding a closed loop is like multiplying by a constant. So you can. So here it's just the idea. There is no details here. So you can add a loop and divide by a constant. Then you have the loop, and then you have three. You have something here, and you. So this is This is called the evaluation of identity. So you have something identity. So the identity is it's like you have a parallel string like that, and this is equal to a sum. That's why you have a sum in the equation. This is a sum of morphism of this form. You have morphism like that, and you do the same here and here, and you get a sum of a sum of product like that. So this is evaluation of identity. You replace identity by a sum of something in another basis, if you want. A basis of this form. And
These are the basis vectors. These shapes are the basis vectors.
Yeah. And in fact, this is an element in the base of a home space. Yeah. You need to fix. In fact, these sum are a sum over a basis of home space, sum of home space, and it's like that. The tetrahedron is the F symbols of this. The associativity. No. In fact the.
So is it not true that if I take this third picture from right? Okay.
This one.
The way I should think about it is I need to write it in terms of the bases of this fusion ring. And then in order to go to right, I need to tensor it with some linear combination of those generators. So I should get that shape, and then I should get that shape, and maybe. But it's not possible, right? Because it seems like the way you get from that picture to any of the things on the right or any of the things on the left, you kind of deform things a little bit.
It's just the idea.
But you said maybe it's this multiplication by constant that allows it.
In fact, this picture was in a paper on graph theory. This has nothing to do with category. This is just a way to illustrate. In fact, we did the proof, and after doing the proof, we realized that the idea was in a picture in another domain of this graph. The interpretation of Thurston for that has nothing to do with category. This is just
yet as a algebra generated by these pictures, you're basically claiming that this algebra has the same structure as fusion.
No.
Isn't that what?
No, this is not. This picture are just numbers. This picture are numbers. We have a closed diagram like that. This means a number. So this is the pentagon axiom. We formulate as a system of polynomial equation, and the variable are scalar, so numbers. So this is not an element of the ring. This is the element of the ring are the label of the edge.
Oh, I see.
And
the labels. Got it.
And the vertices are the morphism.
Now it's more plausible. Any more questions? Okay, if not, let's thank him again. So once again, let me mention something. Postdocs, please, you should come. Orders from Professor Yao.